Good morning, everybody. Welcome to Project Hail Mary Day. We're going to talk about nothing except the movie, right? I saw Project Hail Mary this weekend. Highly recommend the movie and the book, right? Not right now, you've got too much homework and stuff to do, but during break, right? Grab a copy of the book. It's a wonderful read if you like reading. I have not listened to the audiobook. I have no idea. Normally, I will read a book sort of on and off. I read Project Hail Mary in 2 days. Like, I couldn't put it down. And then the movie, which I saw this weekend, excellent. Just an excellent movie on just about every level. Music, visually, pacing, story, all of that kind of stuff. So, highly recommend to anybody and everybody. My wife's a musician and she liked it, right? So it isn't just for nerds. And I was not paid to say any of that. All right. Let's do what I get paid to do and talk. Okay, where are we at? We're at the last unit, right, in optics. What we've done so far is we have dealt with the consequences of Maxwell's equations that tell us that light is a wave, and that those waves propagate, interact with matter, can be focused, can be dispersed, mirrors, lenses, polarization. And now, so we've done reflection and refraction. What we're going to do in one chapter is we're going to do diffraction and interference. Not in that order. We're going to do interference first. So we'll probably spend this week with interference. Probably start diffraction on Thursday, but I'm going to have to carry that on through the Monday we get back from spring break, because so the Monday we get back from spring break is a lecture day, not a lab day, even though it's a Monday. And then, so it's lecture in lab. And then Tuesday, what are we doing? Review for the exam that's taking place on Thursday when we get back, right? So try to keep your physics brain juices going. Brain juice, physics, spring break. I moved the due dates because I messed up. The due dates for the homework are not, there was one due on like the Wednesday or Tuesday of spring break or something like that. That was wrong. Okay? So my normal practice is to not have anything due over spring break. So the homework that's due this Saturday should have been due this Friday, but I kept it on Saturday. And then instead of making the homework due on Tuesday when you get back from spring break, it's now due on Wednesday. Does that make sense? Yeah. Okay, look at Canvas. It should be right now. Thank you to those of you that pointed out, Mr. Baylor, you're mean. You did homework over spring break. I was like, no, it's not what I do. All right. I hesitate to bring up birds because Brandon's in the room. But the plumage, right? I was looking to see if there are any birds out there, and I don't see any. The plumage, so this is a hummingbird, okay? And the lighting on this bird's feathers is something that we call iridescence. It's actually, the different colors that you are seeing here are the result of the interference of light waves as they're coming off of this bird's feathers. We are going today try to explain why birds and insects and other natural creatures and phenomena exhibit this kind of almost rainbow effect that comes about because of interference. We're going to try to explain bubbles. We are going to teach you how to detect a counterfeit bill. And also try to explain why you might not see reflections in some pieces of glass and reflections in others. All of these things are optical phenomenon that are tied together by a single phenomenon. And that phenomenon is interference. Okay? So we need to review just a little bit. Don't panic, but this was something you learned in Physics 2A. And it was all the way back with waves, kind of near the last third of the semester. And this had to do with how waves, and waves only, can overlap in space and time. We call it superposition. Particles cannot superimpose themselves. When you try to get two particles to be in the same place at the same time, they can't overlap. But waves can. Waves go and pass through each other, and they will build on each other in a process that we call constructive interference. Like when two waves are peaking at the same time, they'll build on each other. But what happens if a wave is peaking and another one, for lack of a better word, is troughing at the same time? They just cancel each other out, okay? That's all physics 2A, wave mechanic type stuff. What we need to do is we need to apply this to light, okay? And so what we're going to do, and we're going to start with Thomas Young and the double slit. This is kind of like the OG interference phenomenon experiment, right? Spoiler alert, you don't ever see double slits in nature. Okay, this isn't like a natural phenomenon. This is an experiment that takes advantage of wave superposition and interference. And then what we're going to do is we're going to learn from Thomas Young's results and his experiments and what he was doing, and we're going to apply that to what does happen in nature, thin film interference. And we'll spend most of our time in thin film interference. So I'm going to speed run double slit interference here for you. So before we get into kind of what's going on, let me play a video for you that is hopefully A, going to work, and B, going to show you sort of what the results are of the experiment.
When light passes through two thin slits that are closely spaced and onto a screen, it produces an interference pattern of bright and dark spots. These slides have 3 such pairs of slits, each with a different separation.
You can't see it, but there are double slits there.
Through each pair to show the resulting interference patterns. Here is the setup of laser, slits, and screen as seen from above. This is the pattern on the screen from a pair of slits separated by 0.62 millimeters. This is the pattern from a pair of slits separated by 0.26 millimeters.
Notice what's happening to the pattern.
The pattern is spread.
Thank you.
Here's the pattern from a pair of slits separated by 0.09 millimeters. The pattern has spread even more. So
I don't know if you noticed, but in their setup, right, they had a distance of 3.5 meters, 1, 2, 3.5, right, meters, okay, between where the double slits were and where their screen was. But these slits were being measured in like tenths and hundredths of a millimeter, weren't they? So we're talking about really, really closely spaced slits, but projecting it over a very long distance, okay? So the effect is subtle, to say the least. Thomas Young did not have the advantage of lasers, okay? But he was clever in how he got light to be both kind of one color and collimated. But the essence of what's going on here, right, is that pattern that you saw of the bright spots and then those dark sort of slivers and another bright spot and a dark sliver, what you were seeing was constructive and destructive interference of light waves. In sound waves, we either hear something loud or we don't hear anything at all. In light waves, we either see something, a bright spot, or we don't see anything, darkness, okay? So when the two slits, what they're doing is they're setting up two waves, okay? The light strikes the double slit, passes through the double slit, and now it's like you get two original light waves. And as those light waves come and intersect with each other, depending on which angle we're talking about, okay, we can get situations where the light waves arrive such that one is going up and the other is inverted as they hit the screen, therefore canceling each other out. Or they arrive either both going up or both going down. Either way works. And you get the constructive interference, okay? Now, the thing about this is that it can only happen if light is a what? Wave. This is wave mechanics. This is a wave phenomenon and cannot be replicated by particles. Here's kind of a zoomed in close-up view of a very precise experimental result, and you can really see these bright areas and then these dark areas where the light is being constructively and destructively interfered. This pattern is it's not even a smoking gun, it's the murder scene for interference. You see this pattern, you're like, that's interference. We use some words to describe these things. You run around yelling bright spots all the time and people are going to start wondering. We call it a bright fringe. This line of brightness, okay, is called a bright fringe. Anybody want to guess what the black ones are called? Dark. I led you astray. Yes, okay. Bright fringes and dark fringes, okay, is the terms that we'll use to describe those. Don't panic, don't panic, don't panic. We're not going to actually get into the weeds of this. I just want to point out something, and this is going to be important for when we start talking about thin film interference, which is really the meat of today. On this slide, okay, don't worry about this and don't worry about this one. Let's focus on this middle picture right here, okay? What they're trying to show, so the slits are separated by this distance d. We'll use little d to be the distance between the centers of two very small slits, right? Do you see how they've drawn like a little triangle here, okay? And they're trying to show, like this is a right angle right here. What they've done is they've dropped a line, and so from the line I've drawn this direction, the distance that the light travels to the screen is exactly equal. The light's going up to hit a point on the screen, and these two parts are exactly the same length. But the bottom beam, the bottom wave, has gone an extra distance right here, okay? There's a little tiny bit of extra distance that the bottom wave has traveled. We call that a path length difference, or a PLD, okay? It's delta L in this diagram right here, but we have a right triangle right here. There's a right triangle. Don't worry too much about, this is more like derivation, but I just want to help you understand, right? Here's our path length difference on this side. This is a right angle. We actually happen to know this angle, just accept it. The hypotenuse is d, okay? So what is the path length difference if you know the angle theta and you know the hypotenuse d? It's sine, isn't it? The path length difference is equal to d sine theta. D sine theta. D, the separation between the slits. Sine theta, right, because we're along for the ride with the angle, okay? That's the extra distance that the second wave travels, okay? So what we're going to do in all of our interference setups, so this is going to work for both Young's double slit, which again blew the lid off of Newton's everything's a particle, right? And really showed us that light is a wave and has wave-like properties. But moving forward, whenever we talk about interference, we're going to want to identify this path length difference. Like how there's two waves. Two waves are doing something. And if one of them travels further than the other for whatever reason, we're going to call that extra distance the path length difference. We are going to set that extra distance to a condition that we get to choose. And the condition we get to choose is either constructive or destructive interference. There are other kinds of interference, but we're going to deal with those two extremes. So in all interference, we are looking for a path length difference, and I'll teach you how to do that for all the different situations. And then there's going to be this condition. The conditions is where it gets tricky. They look the same, okay, for all the different types of interference, but their meanings can flip-flop depending on the situation. Again, I'm going to teach you how to sort of get through all of that, right? But let's talk about, so like for the double slit, right? For the two slit interference case, we know our path length difference is d sine theta, right? It's path length difference equals condition. So let's talk about these conditions that we can have, right? The way that we are going to talk about constructive interference is using those two symbols right there, m times lambda. M is a counting number. It's an integer number. Okay, it just goes 1, 2, 3, 4, 5. Okay, it can also have negative sign on it. We'll talk about that in a bit. What m lambda is a multiple of a wavelength. The wavelength distance between two peaks, right? If the distance that one of the waves travels is different from the other one by a full wavelength, like if you take a wave and you just add a wavelength onto it, you get exactly the same thing. A whole wavelength shift is equivalent to just being the normal wave all over again, and that gives rise to constructive interference. You shift it over halfway. Let me see if I can't help you sort of picture this by drawing sine functions. So I'm going to draw a sine function up here, the top one right there, okay? And then I'm going to take, so a full wavelength of this sine function, like peak to peak distance, right? If I keep going with this sine function, if I shift this whole thing over, can you tell the difference? Yeah. Like if I shifted this whole thing, right, I would just end up with something that again looks like a sine function. Okay? I can take all of this and kind of move it back like this, right? Okay? And it looks exactly the same. But now, what happens if we shift it half of a wavelength? If I take this original sine function, okay, and instead take it so that, like I take this and I move it half. Maybe it's easier to look at these equilibrium points, right? So if a half of a wavelength would be to here. So if I take this thing and I kind of shift it over like this. That's a half wavelength shift. I've moved it half. It doesn't matter which way you go, forward or backwards. Okay? A half wavelength shift ends up causing what kind of interference? That's destructive, isn't it? So this is kind of the language that we use to talk about these shifts of the wave, right? So we have m lambda, and then we have m plus a half lambda. So this just keeps m consistent, 1, 2, 3, 4, 5, right? But now we can get 1.5, 2.5, 3.5, 4.5 by writing just m plus a half. So okay, and this only works for two slit. When you see m lambda, this is constructive. When you see m plus a half lambda, that's a destructive case. And so constructive interference, what does that correspond to in the visual pattern? A bright fringe or a dark fringe? Constructive would be a bright fringe, right? We're building the waves together, it's going to be bright. And what would a destructive interference be? The dark fringe. Okay? So you can see here, and I picked this picture on purpose. You see how all the integer ones are lining up with the bright fringes? When they put in m equals 1, it's a bright fringe. M equals 2, m equals 3, m equals 4. You can go negative. It's just a mirror. It's a mirror across this middle zeroth fringe. We call the zeroth, m equals 0, the primary. Okay? So I didn't write 0, 1, 2, 3, 4, but technically you can have m equals 0, 2, 3, 4, I can count. You can have 0 when you're doing the m plus a half. because 0 plus a half isn't 0. So you see here that we have the half integer multiples moving up. And what do all the half integers correspond to? All the dark fringes. Okay. Now, that constructive and destructive interpretation of the conditions applies for two-slit interference only. But the condition itself, m plus a half being a full shift of the wave, m plus a half being a half shift of the wave, and m lambda being a full shift of the wave, that's true no matter what. And this is going to start getting into the weeds here, and you're going to start getting confused, and I'll confuse you first and then pull you out and make myself look like a good guy and a hero and all that kind of stuff, right? Okay, so hold on, just hold on. So our two-slit interference equation is really two equations. It's either m lambda or it's m plus a half lambda. And how do you know which one to use? If you're dealing with a bright fringe, which of these equations are you going to use? M lambda. The d sine theta equals m lambda, right? And if you're dealing with a dark fringe, which one are you going to use? M plus a half, right? The path length difference is the same. It's just d sine theta. Let me warn you about a couple other things I don't think your book warns you about. Remember the distance was really far compared to the slit size? That makes the angle very small. And there's something called a small angle approximation, where we assume that theta, sine theta, and tangent theta are basically the same value. You can do this on your calculator if you want, but you take this, do it in radians mode, but take the sine of very small angles, like do 1 radian, then do 0.1, and then do 0.01. You'll discover that the value of the sine function is the same as the radian value as the angle. This is called the small. It works for anything less than 5 degrees of arc. And so what that lets us do is we can write sine, instead of actually having to calculate and find sine theta, which is usually going to be really tiny, because your setup is one where you have a length L, a distance y on the screen to some point, and this angle is going to be really, really tiny. The tangent of theta is y over L. But because of the small angle approximation, we're going to write sine theta as being about y over L, because that's about the same as tangent theta. Which means in practice, like what I use is this equation. Right? Because the angles are so small, you can actually not have to go find any angles at all. You just use y, the distance that things are separated on the screen. So for example, if they tell you that the difference between the primary and the m equals 3 bright fringe is 2.6 centimeters, let's say, that's your y. It's the distance on the screen between the center and whatever you're looking at, right? And since it's a bright fringe, which equation are you going to use? M lambda, right? But if they then told you instead that maybe your distance between the primary and the 5 halves, right, they'll call that the third dark fringe, okay? Then you know that you're using m plus a half, right? So y is like how spread out the bright or dark spots are on the screen. L is the distance to the screen. And L is always going to be big, like on the order of meters. And Y is going to be on the orders of like millimeters, centimeters, stuff like that. Okay? The key takeaway from this, I'm going to do an example of solving a problem. They're really just kind of plug and chug. But the key takeaway is path length difference, like understanding that one of the waves goes further than another, and the condition that we are trying to meet or achieve. So let's do an example of this, right? So we're told right off the bat 546 nanometers. What is that?
546 times 10 to the negative.
What is 546? It's the wavelength. It tells us the wavelength, right? Wavelengths are always going to be measured in nanometers because we're dealing with visible light here in this section, although we could use others, but our wavelength is 546 nanometers. That's the Greek letter lambda. Again, it's a candy cane that is starting to fall over, and so it sticks its leg out. That's how you draw lambda. Okay? It's the symbol we use for wavelength. 546 nanometers, and nano is what? Times 10 to the negative 9. So that's where we need to know nano. You'll notice, to your terror, nanometers, meters, centimeters. Okay? So watch out. Okay? You got to make sure that you're talking a common language for your units to work out. But annoyingly, you will see this physicist, who is an optical physicist, quite often leave his wavelengths in nanometers. More on that later. Okay. So they've given me some other numbers, right? This 8.75 meters, what is that? That's the L. That's the distance between the screen and where the pattern is happening. The picture you want for double slit is the one I just drew, right? You got the two slits, you got some distance L, and then you've got this screen that's happening over here, right? Okay, you just think of kind of this diagram with the waves, coming up, and you don't have to. I usually don't draw the waves in because it just confuses me, right? Okay, what's the 5.16 centimeters? That's the Y. Do you see how? Okay, they said the distance on the screen from the central fringe to the first bright fringe. There's a lot of words. Central fringe. What M is that?
0.
It's the 0th one, right? Okay. So the central fringe here is M equals 0, right? First bright fringe, M equals 1. You know it's got to be an integer because it's a bright fringe. And what's the next integer after 0? 1. Okay. And then they give us the 5.16 centimeters. That's the Y. That's the distance on the screen. Okay. So what I'm going to do is I'm going to make sure both of these numbers are in meters. Okay. And in fact, I'll meet you halfway, well, more than halfway. We'll convert this one into meters as well. Okay, just to be safe. Although I reserve the right later on to not do this. So this is 546 times 10 to the minus 9. This is 8.75. That doesn't change. And then the 5.16 becomes 0.0516. Okay? Or you could do 5.16 times 10 to the minus 2. Because that's what the centi means, 10 to the minus 2. So there I've got them all in meters. And they are asking us to solve for what? What's the symbol that corresponds to separation of the slits? That's the little d. Remember, we have d sine theta equals m lambda. We have d sine theta m plus a half lambda. The sine theta is going to get swapped out for y over L. So we're working with a bright fringe. So which equation are we going to use? Okay. Okay. Which, again, d sine theta and dy over L are pretty much the same thing. Okay. All right, so we'll solve this for D, not too hard. ML lambda over Y. The M is 1, the L is 8.75, the lambda is 546 times 10 to the minus 9, and the Y is 0.0516. I have an argument with my calculator, and I find that it is 92.6 times 10 to the minus 6 meters. That's how I chose to write it. I actually wrote it internally as 92.6 microns, right? Because the micro just saves me the trouble of writing times 10 to the minus 6. Okay? So there's the slit separation. What is that? It's about, what is that? Almost 10 times bigger than a human hair. How big is a human hair? 10 microns? 1 micron. I can never remember. So it's bigger than your hair, though. Okay? So visible to the naked eye to see that separation and to see the pattern on the screen. Again, don't focus a whole lot of your energy into the double slit. This is not a natural phenomenon. It's what Thomas Young did to show the world that light was a wave, because all of the math that we've just done depends on wavelengths doing what wavelengths do, okay, and how they superimpose themselves. The key takeaway that you need to pull out of the double slit is enough to be able to do the 1 or 2 homework problems I gave you, but really to understand path length difference. And not even just like where it comes from, but more like this concept and idea that 2 waves are traveling different distances. And as they overlap, we can tune those differences to make destructive or constructive light. That's really what we needed to take from this, because what I want to do is spend most of our time on thin film interference. 2 reasons for that. Number 1, it's hard. Number 2, this is what I did in graduate school. Okay? I will not claim very much expertise. Okay? But I consider myself an expert in at least 2 things, professionally speaking. I know how to teach. Full stop. When people say, oh, you're a good teacher, I just say, thank you. I don't try to it's a gift I've been given. I don't want to debase that. I know I can do it, and I can do it pretty well, okay? Maybe that's arrogant or something, but I just acknowledge it for what it is. This is what I'm good at. The second thing I have expertise in is in thin film optics. Okay? And although I haven't really done much with it in 24 years because I focused mostly on my teaching, I keep my toes in the water. I read the literature. It's something like I said, I generate a large portion of my education was spent doing what I'm about to tell you. So forgive me if I get a little bit too much in depth, because I love bubbles. Bubbles are the best, right? Okay? There's just, not only do they bring me joy, right? Like any kid blowing bubbles is a good day, right? Me blowing bubbles, even better day, right? But the thing about bubbles isn't so much like their aerodynamics or their surface tension. All that's interesting too, okay? But where I get fascinated is the colors that are coming off of this soap film. A bubble is, it's air with a thin layer of water and soap, and then more air. It's this sandwich of materials that for some reason is bringing about this incredible kaleidoscope of color. And it goes from bright reflections in the white to dark spots on the bubble that aren't shadows, okay? So we're going from bright to dark and all the colors in between. This is interference. Why did the birds' feathers look the way they do? Why are some green and some blue and some black and some bright? It's interference. Interference is everywhere.
So like I remember like doing stuff in like elementary school where like the longer the bubble is like a thing, it'll get more dark spots.
Yeah, I'm gonna show a video of that. Yeah, no, I paid Chris to say that because that's where we're going. Thin films are everywhere. They are literally everywhere. What's a thin film? It's in the name, right? But the problem is, what does it mean to be thin? It's thin compared to the wavelength of light that's striking it. This is a film of oil on water when illuminated with white light. This is like kind of like. Have you ever? Well, no, it never rains in Fresno. Have you ever been walking through the parking lot and you see a puddle of water in the parking lot, and then there's like this sort of rainbow sheen on the surface where the gasoline and the oil and the coolant from cars is maybe leaked out and collected or something like that? It's very polluted water, but it's got that sort of rainbowy sheen on the top, okay? That's coming from a very thin layer of oil floating on top of a much thicker layer of water. So in that situation, you have air, and then this very thin layer of oil, and then a very thick layer of water, okay? We call it the substrate, the material that the thin film is sitting on. So you have your substrate, your thin film, and then you have we call them superstrates, but you don't need to. The incident material, okay? Where the light's originally traveling on, okay? So I think, Chris, is this kind of what you were talking about? Like the longer the bubble sits around, the thinner it gets at the top here, okay? So this is a soap film that's being held inside of a ring. And you can see, look at the very top where it like looks like there's no soap film at all, right? It's totally black. If there were no soap film up there, this bubble would have broken, okay? It wouldn't exist. But there is film up there. It's just so thin that there is no constructive interference happening whatsoever. And so the light is completely canceled out. This soap film is thickest at the bottom. And you see how it kind of gets muddy? It's gone from thin to a more thick film, and so we're not getting as much of the interference. But then we get some pretty bright colors in the middle, where the thickness of the film is kind of ideal. Well, in the case of that bright yellow line, that thickness is ideal for yellow light to get constructively interfered. And where you see red, that's another place. And you can see red multiple times. So there must be multiple thicknesses that cause this to happen. This is all thin film interference. The lenses of your phone, right? If you take your phone out and you kind of hold it up to the light, and as long as you don't have like a special protective cover over them, if you turn it just slightly, you might see, not on the surface glass that's protecting the lens, but down inside, looking at the lens, you might see greens and purples coming off of that lens. There's coatings on those lenses, very thin coatings that cause light to be, we call it an anti-reflective coating. And you're seeing it here in this picture. Do you see how the reflection of the light in this glass looks purplish? Well, how do you get purple as a color? What two colors do you have to combine? Red and blue. And where are red and blue on the electromagnetic spectrum? Opposite ends, right? So what this film is doing is it's doing a really good job of anti-reflecting all the colors in the middle, but not quite getting the two ends, which is very common for a thin film invisible light, okay? So why would you want anti-reflective film on your camera lens? When you get reflections inside of the camera lens, that's called lens flare. So unless you're J.J. Abrams in the early 2000s, okay, you want to eliminate lens flare as much as possible. It's a artifact of capturing light in a camera lens system, and you want to suppress it, okay? Although some movies and video games and stuff have a switch for, oh, bring back the camera flare. I'm like, off, it's a visual defect, off, right? Okay? I'm not going to do that. All right, so I hope I've sort of primed you, right, for why this stuff is like important and cool. It's like, have you noticed it's cropped up in biology and optics and natural disasters or man-made natural disasters and yeah, okay. So we need to talk, okay, one more example. I never know if this is going to work because I fully realize I'm asking students, okay, for money. Does anybody have a $20 bill?
No.
Because I don't bring my wallet to class. $20 bill? Okay, Jack has a $20. Thank you, Jack. I would like everybody to witness right here that Jack is giving me a $20 bill of his own free will and that he will get it back, and this does not constitute a bribe. Right? Right? Okay. Why do I have a $20 bill in my hand? Right. All right, so let's see if the overhead projector turned on. Okay. All right, good. We're seeing $20 bill. Okay. What I want to show you on the $20 bill is this number right here. Okay. Focus. There we go. Okay. We're going to see if this works. This might not pick up on the Elmo. I haven't tested this particular Elmo, but I'm going to turn the 20. See if I can get it to focus. Do you see what's happening to the color of that 20 as I rotate it? So do you see how there it's kind of reddish? And then it's going to go out of focus. Do you see as I rotate it, it kind of turns greenish and then turns black? Okay, I would like everybody to witness. I'm giving this $20 bill back to Jack, okay? Right, with the full understanding that there was no bribe involved. Jack, look at the 20, like rotate it, like kind of tilt it in front of your eyes. Is it changing color? Yeah, okay, it changes color quite dramatically, okay? I believe this exists on the 20, the 50, and the $100 bill. What they've done is they've printed in a special ink that causes the change in color depending on what thickness you happen to be looking through the thin film in that ink, okay? It's an anti-counterfeiting ink because it's actually kind of hard to print something that precisely that can change color that way. It's not the only thing that exists in anti-counterfeiting measures. The $100 bill, for example, if you've ever done retail, they teach you to hold it up to the light to see that strip in there. There's some UV inks in the $100 bill. If you have a UV pen, you can run it over the UV inks to see if they fluoresce. There's other things, but for the 20, they didn't put in the more expensive things. They just did that. Well, there's a couple other things in the $20 bill. But again, right, thin films are everywhere. If you are wearing glasses right now, there's a thin film on your face, okay? Because you probably opted for the anti-reflective coating on your glasses, okay? I, like you know, used to wear glasses. And when I first started teaching, okay, think poor graduate student in college teaching freshmen and sophomores, physics, all that kind of stuff. I was upset. I was mad because here I was doing what I thought was a really good job of explaining physics to people. I really wasn't. I was actually kind of doing a bad job of it. But I thought I was doing a good job. And nobody was looking at me. One of the things that humans are either very uncomfortable with or find deep meaning in is eye contact, right? Okay, it can either scare people or it can get people hooked, right, or involved in a conversation. So if you've ever had a teacher that just never makes eye contact with you, right, is more than comfortable talking to the board or to the sides of the classroom or to the ceiling, right, you've probably felt kind of disengaged in that class. Right? But a teacher that makes an effort to look at you, right? Okay? Tends to be rated, even if the students don't understand what's going on, tends to rate them as being more friendly or engaging or whatever, right? So here I was trying to make eye contact constantly with my students, and nobody was looking at me. They were looking at the board, they were looking at the ceiling, they didn't have cell phones at the time, so they were just falling asleep, but they weren't looking at, and finally one day I kind of had enough, and I'm like, why? Room 300 students, okay, in a lecture, right, okay? And I finally just said, why is nobody paying attention to me? And they're like, Mr. Baylor, we're paying attention. We got this. And sure enough, they answered, like they're like rattled off some stuff. I was like, oh, okay, well, but nobody looks at me. And they're like, yes, we do. We're looking at you. I said, granted, it's not much to look at, but like, I'm trying to maintain eye contact and you guys are just, and they're like, I don't, and finally one student put his hand up and he says, Mr. Baylor, I think I know what the problem is. We can't see your eyes. I went, what? He says, take your glasses off. I took my glasses off and everybody looked at me. Right? Put my glasses back on and they started. The lights in the lecture hall, like a theater, like I was standing on a stage and it was stadium seating and all that kind of stuff. The lights in the room were hitting my glasses and reflecting, and all that anybody ever saw was like when somebody's wearing sunglasses, that reflective coating, right? And you can't see their eyes, okay? People wearing sunglasses tend not to talk to each other. They're standing around in a group, but they're not actually looking each other in the face. Why? Because they can't see the eyes of the other person. So they're looking at the whatever, right? Okay, they're talking, they're communicating, but they're not actually like looking at each other. So at that point, I realized what was going on, and the very next pair of glasses I got, again, we're talking, I'm eating top ramen and cans of chili, right? Okay. I scrimped and saved and just ate more top ramen so that I could get anti-reflective coatings on my glasses. It was night and day. Like people just kept, just in lecture, were talking to me and interacting, looking at me, all that kind of stuff. So yeah, it is a quality of life issue, and I highly suggest that you get that. Anyway, what the heck is going on? Okay. Sorry, I had to center myself. This is too cool, and I was about to explode. We have to deal with index of refraction. We've got to deal with what happens to waves when they try to go into other stuff. And then we need to put that together with path length difference and the conditions. So there's a lot going on here. Let me warn you ahead of time. This is so like back in lenses and mirrors, the hard part is not the math. It's what? The signs. You live and die by the signs. That happened yesterday in lab, right? People were just getting stuff wrong. I'm like, check your sign, right? Okay, it's the signs, you live and die by them, right? In interference, especially thin film interference, you live and die by the setup. The math itself is actually stupid easy. It's getting to the point where you can apply the correct equations that makes all the difference. So concentrate on the concept here. First piece of the puzzle that we have to talk about is what happens when waves hit things. If a wave, let's just look at the strings for a second. When a standard transverse wave hits a solid change in medium, like a wall or something, the bounce, the reflection of that wave is inverted. Notice on this slide, they're calling it a 180-degree phase change. Bless you. What I've drawn up here for the destructive sine waves represents a 180-degree shift of the phase of the function. That's really deep, but basically 180 degrees means m plus a half. Okay, so if you see 0-degree phase shift or 360-degree phase shift, what's that? That's m lambda. And what's m lambda? Constructive or destructive? Constructive. Okay, right? So now we have just another set of terminology that's used, right? And it's grounded in the mathematics of what sine and cosine functions do, okay? But if you shift a sine or cosine function 180 degrees, you get destructive waves, okay? Of course, you can shift it any number of degrees or radians you want. We will stick to 180 or 360/0. Okay? Those are the two extremes that we will have. And then it gets more annoying. In some websites, ChatGPT and other things like that, it might say pi or 2 pi. It's the same. Okay. All right. Notice on this screen right here, right? the first material's index of refraction is low, and the wave is bouncing off something that has a higher index of refraction, if the index of refraction between the material the wave's traveling in and the material it's trying to go into / bounce off of is a low to high, you get a 180-degree phase shift. The reflected ray is 180 degrees off the original ray. That's one of the rules. We'll get all this down onto a single page, I promise, okay? If the wave encounters a boundary or a change in medium where the wave is free to wiggle, then you'll get a reflection that is in phase, or no phase change, or 0 degrees, or 360 degrees, or 2 pi, right? Those are all the same way of saying the same thing. There's been no phase change. Even though it may have shifted a full wavelength or a full phase, there's no difference anymore, okay? Notice, optically, what needs to happen. What's the transition? High to low, right? So low to high, it flips 180 degrees. High to low, no flip. Stays the same. Okay? Again, we'll write all this down. Okay? Here is the beginning of the whole enchilada. Why do I say that? This is all that you will be asked to know and to keep track of. In fact, there's a lot more going on, okay, in the optics of this, right? But, and I'll give you a taste of that later. Not that I'll make you do anything. I'll tell you a story about my graduate work. But let's try to kind of understand what's going on with the light as it enters a thin film. We're going to put on hold for a second, okay, that there are these phase shifts happening. Let's just talk about the rays of light, because we know enough now to be dangerous. We know that when light hits a change in index of refraction, there's going to be reflections, there's going to be refraction into that medium, right? So on and so forth. So what we've outlined are all the important pieces of this change, okay? Again, ignore all these phase changes for just a second. Light's coming in. And when light hits a surface, it's going to reflect and refract. So they labeled this first reflection as number 1. So the light comes in, bounces off, we've got that. But it also refracts into the thin film, right? We've got a substrate down here, we've got the thin film in here, and then we've got this incident material on the top, okay? So light will pass into the film and then hits another layer, another change in medium. And so it's going to reflect again and also refract. We will always not care what's going on over here. Okay? Don't worry about that one. Okay? We want the first reflection, and then we want the second ray as it comes back out. You don't have to do Snell's law because we are going to simplify. All of the thin films that you will deal with in this class will have the light be incident normal to the surface. They'll come in at 90 degrees. When you introduce the angles, you have to do Snell's law stuff. Okay? It's not terribly difficult, but I'm supposed to teach you about Einstein's relativity and quantum mechanics and nuclear physics. And if I started teaching you everything I know about thin films, we'd be here for the next 4 years. Okay? So the problem with normal incident pictures is that the light will come down. The angle of incidence is 0 degrees. Remember we measure the angles from the normal? And so the angle of refraction is 0 degrees. and then it bounces directly back up along that same line. Believe it or not, I drew a line there. And then it exits right along exactly the same ray, right? This picture doesn't help us understand what's going on, right? It's got too many overlapping things going on. So we draw a picture that looks like this. In fact, the picture that you will always use will consist of two parallel lines that represent the two boundaries for the materials, with the film in between. You don't have to label it flim. You don't have to label it, okay? You just need to understand that between the two lines is your thin film. And then what I do is I draw a ray coming in and bouncing, and then I don't bother with any refraction angles or anything. I just draw a second ray, kind of doing the same thing on the bottom. It's the visualization for thin films. It's a lie because for you guys, the angle is always 0 degrees, and so it should all be straight up and down. But for clarity, for keeping track of things that are going on in the problem, draw it like that, okay? If you want, like, the simple way to draw this, really, is just to draw two lines and then just put two check marks on it, right? Because that's basically what this picture is. You need to capture the fact that there are two rays, okay? One ray that bounced off the top of the film and another ray that bounced off the bottom of the film. Okay. Remember what we did with the two-slit experiment? Everything in interference came down to two things: a path length difference and a condition. Let's tackle the path length difference first. What is the extra distance that the second ray travels? By the way, we only have to figure this out once, and once we've got it figured out, we're golden. We can apply it everywhere. But let's figure it out once. Notice that they're using T as the thickness of the film, not time, but thickness of the film. Okay? How much further does the second ray travel? 2T, good. It's really going straight up and down, isn't it? It's not going sideways, so we don't have to figure out any of the geometry or the triangles. It's coming down a distance T, and then it bounces off the bottom and comes up a distance T. So, write down what, you can write down whatever you want. Be sure to write down what I put in the box, okay? I'll box the most important part when we get there. So the path length difference equal to condition, right? Okay. The path length difference is 2t, isn't it? Okay. What are the conditions? Hint, they're the same as the double slit. What two things do we want these waves to do? We either want them to constructively interfere or destructively interfere. So the condition can be either m lambda or m plus a half lambda. And here's where the complexity comes in. Those do not mean what you think they mean. Never know how to teach this, because there's different people's brains have different ways of understanding what I'm about to say. So I'm going to try this several different ways, and I'm going to hope one of them sticks. Okay? Do not assume that m lambda is constructive and m plus a half is destructive. That is no longer true. Let me show you why. Let's go back to this picture. We've got air, we've got material, and we've got air. What's the index of refraction of air? About 1, right? And let's just say this is a soap bubble, water, okay, 1.33, and then n equals 1 again, right? Okay, oops, not 1, n equals. All right, so let's go back to the bounces. Remember these bounces that we had here, right? What does a low to high transition do? It means that there's a 180 degree change. And what does a high index to low index? What does that do? Zero. Okay? So on this first bounce right here, came in, bounced. We're going from n equals 1 to 1.33. What kind of transition is that? Low to high. A low to high is what? 180. Okay? Notice how they wrote 180 degrees on that ray. Okay. On the second bounce, we're looking at this interface down here. What kind of transition or interface is this in terms of the index of refraction? It's a high to low. So what does the second ray do? It's 0 degrees or no phase change. You do not have to worry about it coming out. This right here is not a bounce. Okay? This is a refraction. There's no changes upon refraction. In truth, this ray keeps doing this. Okay? And it attenuates, it loses energy as it travels. Okay? So there's actually lots of things going on here that we're not going to get into. So let's just, again, we have control over just about everything in here. The thickness and the conditions and all that kind of stuff. If we tune the thickness of the film such that the path length difference is such that we maintain this phase relationship. In other words, we don't do anything to this relationship. What will these two rays do? One of them is 180, one of them is 0. When they come back together, what are we going to get? Destructive interference. Notice I said all of that in a language of, are we going to alter the phase relationship between the waves? The way we can alter it is to change the thickness of the film. If we change the thickness of the film, we can change the path length difference. And if we change the path length difference such that we alter the phase of the second ray so that it is now 180 degrees different from what it was, then the first ray will be 180, the second ray will be 180, and if both of them are 180, what do we have? Constructive interference, because they're both 180. I'm going to do this a lot, don't worry. Okay? That's your first time, but there's a lot to hold on to there. And it's all conceptual, it's all physics. There's very little to no math required to work this step. We're going to write math down based on the results of our concept, but you have to do this for every single problem. There is no short version of this. For every thin film, you have to look at what the first and second rays are doing. How are their phases changing? And then you tailor the equation to what it is you want to do. M lambda and m plus a half lambda are always consistent in what they do. What they do never changes. Okay? So what m lambda does, so this is the do column, okay, is it says no change to the relationship between rays 1 and 2. When you put down the condition of m lambda, you're telling the mathematics and the physics of the system to keep whatever's going on, keep it the same. Because the thickness of this film, if it's equal to a multiple of a wavelength, you're going to get a full wavelength coming down, you get a full wavelength coming up, and nothing is different. Remember, full wavelength shifts don't do anything. They keep waves with no phase change. So what m lambda means in thin films, what it says, what it does is no change. But the meaning of no change depends on the situation. We'll get to that in a second. So if m lambda means don't change anything, what does m plus a half lambda mean? Change it. Change ray number 2 by adding 180 degrees to its phase. Again, that plus half means 180, right? Okay, so let's do some practice. I'm going to do this. Okay, so let's do, what I'm going to do is just going to kind of do a bunch of these, right, where we've got these two rays bouncing off, right, and we need some indices of refraction. So let's do 1, 1.33, and 1.52. So this is air and then a thin film of water on glass. Okay, so we need to determine what the waves are doing naturally or just because of the materials. And then we need to figure out what equation means what. Because the meaning shifts, but what they say or do remains the same. So, first step, first bounce. What's the phase change, if any? Top bounce, we're going from 1 to 1.33. What kind of change is that? That's a low to high. We're going from 1 to 1.33. So what is that? Plus 180. So what you want to do is just write 180 on that first wave. If there were no change, it would be 0. Okay, on the second bounce, 1.33 to 1.52 right here. So what's going to happen? That's a low to high, isn't it? We're going from 1.33 to 1.52. That's a lower to a higher. So what is it going to be? 180. All right. Oh. Hang on for the ride for just a second. There's going to be an index of refraction here. I'll explain it later. Okay. This equation right here, okay, with the m lambda in it, what does it do? No change, right? This says don't change the relationship. I'll even write it down. No change. And so if there is no change in the relationship between those two waves, what are they doing? Constructive or destructive interference? Why is it constructive? They're the same phase. They're both 180 degrees out of phase from the original, but they're both in phase with each other. In other words, they're the same number, 180 and 180. So this is constructive interference. 2nt equals m plus a half lambda. What does that say? It says to change it, right? Remember over here, what do? Change number 2 by 180. So if we change number 2 by 180, we say plus 180 to this, then what does this equation become? We'll have 180 for the first one, we'll have 360 for the second one. Are those in or out of phase? Out, so therefore destructive. Let's go back to the soap bubble. One we just did. We'll replicate it, right? First bounce. This is air, water, air. First bounce. What's the phase change? What's the transition? High to low or low to high? Low to high. What's a low to high? 180. Second bounce. Low to high, high to low. It's a higher to a lower. And what does higher to lower do? No change. 0, right? So, what does 2nt equals m lambda do? No change. Can't spell. Okay. So if we do nothing to change this relationship, what are these two rays doing? They are destructively interfering with each other. Why? They're out of phase. One of them says 180, one of them says 0. This is now the destructive case, right? I'm going to be consistent. Red, doom, destruction. Okay? And then 2nt equals m plus a half lambda. What does it say to do? Change it. And if we change this by adding 180, it now becomes constructive. What does 2nt equals m plus lambda mean? Good. It means no change. I'm glad you didn't say, well, it means constructive. It doesn't. Because constructive and destructive depend on the physics of the situation. The equations mean no change or change. And by change, we mean add 180. But their application is different for every single situation. Let me clean up this. I mixed all my colors up here. No. That was plus 1, like that. There we go. Okay. So now we've got consistent coloration. Okay. Let's do another one. 1.52, 1.33, and 1. Glass to water to air. Okay. First bounce. It's a higher to a lower, so that means no change, right? 0 degrees. Second one? Also 0. We're going from a higher to a lower index, right? 1.33 to 1. If we leave everything alone and we don't change anything, what's this one going to be? And if we change the second one by 180, do that every single time. You will be safe if you do that process every single time. Am I asking you to think?
Yeah.
Yes. Okay? You must think. Okay? Your way through. You never know when you might be called to explain this. Not that I would ever do this to you, but in graduate school, one of my advisors was teaching a class on thin films. I took this class for completeness reasons, right? I'm not sure I ever really needed it because I already knew everything that was going on because I had been doing research for like 3 years on thin films. One day he had a personal issue. He had to deal with something at home. He walked into the class and I was sitting there with like 4 or 5 other graduate students that were taking this class. He handed me the textbook. He said, "David, please teach the class for me today." And he walked out. You never know when your expertise might come in handy for what's going on. We will pick up with this on Thursday. We're going to do some examples, and then I might get a little distracted. We'll see. It's going to be worth it. I promise. I would not waste your time. So it'll be a distraction for good reason. I will see you on Thursday.